Hey there, it's Jason from Codemanship with another technical video diary entry. We're going to be looking at some more code. So on the Codemanship Twitter account yesterday, I posted a teaser, a puzzler if you like, based on a multi-threaded and asynchronous version of the famous Mars rover TDD kata, which I've demonstrated many times and you may well have come across it yourself. Don't worry too much about the problem itself, it's very straightforward. The idea is that we're going to write some code that drives a fictional Mars rover over an idealized grid of XY coordinates that represent the surface of Mars. And we send it sequences of instructions, basically individual characters, R to tell it to turn to the right, L to tell it to turn to the left, F to make it go forward one square in whichever direction it's facing, and B to make it go back one square. Now, in the usual simple version of this, we send it the instructions and it executes them straight away. It executes them synchronously and then returns control. And that's very easy to test. But in this rather fiendish version, it doesn't do that. As you'll see, we have a go method that accepts a sequence of instructions. Let me just highlight that code. But instead of executing the instructions, what it actually does is it puts them on a queue. And then there's a separate method called run, which runs in a separate thread, which pulls instructions off the queue if there are any, and then executes them one at a time, also giving a little output to show what the state of the rover is at the end. And then it sleeps for 1,000 milliseconds. Basically, it sleeps for a second. So every second, it pulls a character off the queue and executes that instruction. And we've got a little hash map there mapped onto methods that actually make the rover do things. And if we look at the little command line program that I've rigged up here, this little test harness, when I run this, basically it's gonna prompt me to enter a sequence of instructions, and then you'll see that it executes those instructions after the fact, one every second if there are any. And there's also an X. If the instruction is X, then it will actually exit the program at that point as well. So I'm just going to demonstrate this so we can test it by hand. So let's run that program. Hopefully it's all working. Fingers crossed. You never know with multi-threading. Okay, so we get a little message there to enter instructions. So let's enter a sequence of instructions. Let's turn the rover to the right and then tell it to go forward a couple of squares. So if it's facing north to begin with, it will turn east and then move 2 squares in the X direction. So we would expect the final coordinates to be 2, 0, where X is 2 and Y is 0, and it to be end up facing east. So when I hit this, it's going to not execute those straight away. It's going to stick them on the queue, and then that run method on a separate thread is going to pull one instruction at a time off the queue and execute it, and then give us the output. Okay, so off it goes. There we go. It turns right, goes forward. And so we end up facing east at coordinates 2, 0. And then it's awaiting more instructions. And if I enter an X, it should exit the program at that point. There we go. So it's a pretty straightforward program for multi-threaded logic. There's only 2 threads, basically. There's a main thread, and then there's the run thread, the one that's actually executing the instructions. Now, the purpose of the exercise, as vague as it was, I was just noodling really, was to see if I can get people thinking, including myself, thinking about how we might need to design our rover to make it unit testable. Ideally, when we're writing unit tests, we want all of our tests to be synchronous, because when they're not, when we have to spawn extra threads, it can create problems. So first of all, let's take a look at a little unit test that I started to rig up. So just to prove, when we call the go method, the rover does nothing. It just sticks those instructions on the queue. So this is a test for turning the rover from north to east, turning right. So let's run this test, and you'll see when we run this, it's going to fail because we haven't actually, let me just show you the message there, we haven't actually gone anywhere. We haven't turned the rover at all or moved the rover. So we need to figure out a way to run those instructions. Now, here's the problem that we've got. If I say, okay, let's run that, then we have a bit of a problem, which is that we get an infinite loop, as you'll see in a minute. So the test will run, and it will run, and it will run, because that while loop, if we take a look at the rover code here, that while loop will keep going while the thing is running. Okay, now to stop it, we need to call a method called stop. So running basically is just a Boolean flag. We set it to true when we start the run method, as you can see there. And then because it's running on a separate thread, on the main thread, if we call this stop method, it will set running to false, and then that loop will terminate. We can't synchronously call the stop method because we're in an infinite loop. So it's going to wait for the infinite loop to end before it does anything else. So if I just try that in my test here, rover.stop, this isn't going to make any difference because we'll never get to line 14 from line 13 because it's an infinite loop at line 13. Off we go. And there's our infinite loop. It does execute the instruction, but then it just keeps going round and round and round with an empty queue. And nothing else is happening. So let's terminate that process. So that's our problem. We can't at the moment easily test it synchronously. We could try testing it asynchronously. So for example, if I spawned a new thread and called the run method from inside that new thread, so let's start that. That will solve the problem of the infinite loop because we'll call the stop method, it'll go, oh, okay, I'm done now. And it will probably execute the instruction as well. But there's another problem, which is because it's now asynchronous, it's going to return control immediately, which means we will probably get to our assertion before it's actually found the instruction and executed it. So even though it probably does actually do, I checked in the debugger, it does actually perform the action that we want it to perform, but we've already evaluated the assertion before it does that. So this is a problem with asynchronous tests. So let's try running that now. So we won't get an infinite loop, probably, but our test will fail because we get to the assertion before the action has been performed. So we're kind of back where we started, where it's expecting it to be east, but it's still north at that point. It will eventually become east, and the thread, the second thread that I spawned there will terminate because we've called stop. So the next time it goes around the loop, running equals false. But we get to line 15 too soon, basically. It hasn't done its work. So that's kind of the challenge. What do we need to change about the design of the rover, the design of this program, that would make it possible for me to queue up some instructions, execute those instructions, and then check that the result is what we expect it to be. And in order to do that, ideally, rather than messing around with multi-threading in our tests, there are ways that we can do this. We could put wait conditions and all kinds of other things in there. There are ways we could do this, but we would end up with quite a messy test and potentially quite a flaky test suite once you get multi-threading involved. So I'm not a big fan of doing that. Ideally, we want to be able to test all of this code in synchronous tests, just on a single thread. So that's the challenge. I'm just going to pause the video now, and I'm going to come back in a few minutes when I've had a little play, and we're going to see what changes we could make that would make this now a synchronous test. Okay, so I've done a bit of noodling here, and what I've done is, so the problem was that we didn't have, in a synchronous way, we didn't have a way of changing the value of running to false to make our while loop terminate. So what I've done is I've introduced a class that controls that. It knows whether or not the thing is supposed to be running, called a control. We can probably think of a better name for it, but since it's about control flow, I just went with that for now. And the control is being injected into the rover. In other words, we've got inversion of control. We can control the control from the outside. So in my now synchronous test, I'm using Mockito to create a stub control that's going to return a sequence of true-false values. So the first time it returns true. So we go around that while loop once, which is all we need for this test because we've only got the one instruction. And then the second time it'll return false, which means that the while loop will terminate. So I've just run this, but I'll run it again for you. And as you'll see, off it goes. It terminates as we would expect. And when it gets to the assertion, it has executed the action because it's all synchronous now. Puts the instructions on the queue, then executes the instructions in a loop that we're controlling when it terminates from the outside. And generally speaking, when it comes to making asynchronous code testable synchronously, usually it's about inversion of control. It's about essentially controlling the flow of the logic from the outside that's happening on a separate thread, so that it can all happen synchronously on one thread. Okay, so that's one test for one instruction, pretty good. But let's do a bigger test. Let's do a test for a bunch of instructions and see where that ends up. So I'm going to pause the video again, rather than you watch me typing, and I'll write another test for a sequence of instructions. Okay, so I've written a second longer test here, where we tell the rover to turn right, then move forward twice, then turn right again and move backwards twice. And it should end up facing south at position 2, 2. The test is passing. If I just run this test, you'll see that there is still a problem. Let's run that test and you'll see what the problem is, hopefully. So at the moment, this thing is rigged with a sort of a delay. It sleeps for a second between executing each instruction. And if we had a whole bunch of these tests, that would become a problem. Our test suite would be very slow. So we also need to consider how we could get around that, this built-in delay that we've got here on line 46. Well, really, it's all of these lines here are all part of that. And it's a similar kind of principle. We're going to use inversion of control so that we can substitute a shorter delay, maybe a 0 delay, so that we can test the logic. We can test the delay separately in some other test if we wish to, but what we don't want is hundreds of tests potentially that take many seconds to run, because then our test suite is going to be slow, and you know how I feel about that. So again, I'm going to pause the video. I'm going to do a little refactoring. We'll introduce a bit more dependency injection, some more inversion of control, so that we can control the delay, essentially. Okay, so I've done a bit more noodling. What I've done is I've introduced a class called the timer. So the sleep code is inside the timer. If we just take a look there it is. And take a look at our rover. Basically, it's using that timer, and that timer is, again, like our control, it is being injected into the rover class from the outside. That means we can control it in the test. So in the test, I've just created a mock timer. So when we call sleep, it's not actually going to do anything. It's not going to pause the program. So when I run my tests now, let's run them all. They should run pretty speedily. There you go. So really, the purpose of this exercise was to demonstrate how we can use mocks and stubs, for example. We can use dependency injection and inversion of control for all kinds of reasons. For example, to test unit test code that has external dependencies, to fake parts of the system that we're going to make later, fake it till you make it. And also when we have, for example, random or data that we can't control in our test, to make that data so that we can control it in our test. And that's kind of what we're doing here. We can, for example, control when the loop stops, and we can control how long the delay is. In this case, we want it to be nothing for the program. But in the actual command line program itself, if I run that, we've still got the original delay. So we're using the actual implementation of timing rather than a mock timer. So if I enter some instructions here, like R forward, and then R back, the same instructions we had before, it's still doing 1 a second. It's just not doing that in the test. So that's another really useful sort of way in which we can apply inversion of control and dependency injection, is to make code that can't easily be tested synchronously or quickly, to make it easy to test it synchronously while still retaining its multi-threaded nature. But the multi-threaded nature of it is controlled entirely from the outside. It is usually best if, as a general rule of thumb, code that's going to be run on separate threads shouldn't know it's being run on separate threads. That's the idea. That's somebody else's problem. Okay, so there you go. There's a little demonstration. You can find the original code, so if you want to tinker with it. People have pointed out there are all kinds of ways we could have done this. For example, in our program, the special character X stops the program. We could have moved this code into our rover, for example, so that if it gets a sequence of instructions that ends with X, then it will terminate the loop there. So that's another way in which we can control it from the outside, is essentially to have some kind of terminator that says, okay, when we hit this, we stop. And then we can control that in the test by controlling the data, the input data. So there you go. Hopefully that's been of some interest or of some use. I'll post a link to the original GitHub repo so you can play with the original version of this and do your own refactorings. I hope you're staying safe. If you're enjoying these videos, ring the bell for notifications and subscribe to the channel. Please like this video if you enjoyed it, because YouTube seems to, their search engine seems to like that. And I will speak to you all again soon.